Morning everyone. So we're going to finish off our final review in looking at our Redox chapter. Hopefully some of these concepts are still really fresh in your head here. We looked at this section here on electrochemistry. It was this interplay between electricity and chemistry. At first what we did is we dealt with spontaneous chemical reactions. We used the chemical reaction to actually provide an electrical voltage. That was a Voltaic Cell. And then towards the end of the chapter, we actually were focused more so on the chemistry. There may be a reaction that I'm interested in running. Right now here, because of the strengths of the oxidizing agents, reducing agents, for whatever reason it's non-spontaneous, we can actually use electricity as actually the push to actually get the reaction going. That was actually a non-spontaneous reaction. Regardless, though, we still use the same redox table. We started from the top left for the strongest oxidizing agents, for the strongest guys that gain electrons. It's just by the time we found your matches, they had actually switched places. So it's this interplay between electricity and chemistry. Our main reaction is a redox reaction. A redox reaction is actually two halves of a whole equation. The oxidation part refers to a loss of electrons. So something is willing to donate electrons, very similar to our acid-base chapter. This is something that transfers electrons away from it. While I have something that's doing the reduction, another chemical that ends up picking up the electrons, that's the other half of the equation. I cannot have a reaction that both people oxidize or both people reduce. If both people want to oxidize, I'm going to have a lot of free electrons in nature, although the half equation can have a lot of electrons balanced. We know charges are unstable. Unless I have someone willing to pick them up, it's not going to happen. Similarly, if I have two things that are reduced, two things that are willing to actually wait for electrons, but if no one's willing to give it electrons, then it can't actually gain electrons either. So again, we had a lot of different memory aids here. We can say here, Leo the lion says grrr, just spelled jr like this, okay? And therefore you can say a loss of electrons is oxidation, or a gain of electrons is reduction, and they have to happen together. Remember, when we're asked to sort of label who got oxidized, who got reduced, and as well as your agents afterwards, we are looking at the reactants. So let's just do as an example here. Let's say zinc reacts with H plus and ends up forming Zn plus 2 and just H2 like that. Okay. For a simple equation like this, what you would do to label who's oxidized, who's reduced, again, we are only focused on the left-hand side. After the electron transfer has happened, we end up creating Zn plus 2 and H2. Don't really care about that, and I know this one here isn't quite balanced yet. But let's see if we can label it. Zinc goes from an oxidation number, an oxidation state. In the elemental state, elementals are given 0, while later on it's actually a plus 2. Anytime your oxidation number actually increases, you can actually say the change in oxidation number is actually bigger than 0. So oxidation number increases. Oxidation number is actually bigger than 0. It's positive. That one there is actually an oxidation. So how do I get my charge to go up? It's for me to have lost electrons. Zinc currently had a bunch of electrons. Who did it pass the electrons to? He actually passed it just to the other reactant. It's the zinc that underwent the oxidation, so zinc gets oxidized. Who picks up the electrons? Well, H plus is present. It goes from rough plus 1 and down to its elemental form here 0, although I have two atoms with H actually going downwards here. So that's going to be a reduction reaction. H plus, its oxidation number goes down, so that process there is called a reduction. So the change in oxidation number is less than 0, or you can say the oxidation number decreases, another way of framing that there. It's the chemical that was involved, it's the H plus that was reduced. So electrons have just transferred between these two reactants. After that happens, we just happen to create Zn plus 2 and H2 like that. In terms of our agents, agents are used to actually help. So if I have an oxidizing agent, it's something that I have that actually helps something oxidize. So in this situation here, if I have the Zn being oxidized, who's present that's willing to let the Zn lose electrons? Well, it has to be the one that's actually willing to gain the electrons. So the H plus, actually the chemical that's being reduced, is also the oxidizing agent. It allows the Zn to oxidize, and in a similar fashion, because the H plus is reduced, it's the Zn that's actually our reducing agents. If I ask you for a definition of these agents, I want you to tell me their job. So oxidizing agent helps something else oxidize, reducing agent helps something else reduce. Just a hint for yourself to figure out, well, who is the oxidizing agent or reducing agent? You figure out sort of the opposites. Okay? even though in reaction, it might very well be, let's say it's manganese, I go from a +7 state down to a Mn+2 state. Oh, this one here itself actually got reduced. You still quote the entire compound. It's the permanganate ion that actually got reduced. The reason why I include this here is that's when I did my titrations here. A very, really strong oxidized agent like permanganate. This one actually starts off from a purple color, and it ends up forming a colorless color here. Usually we need to have some indicator, some endpoint here, but if the chemical itself actually shows its color change, when that color change happens, I know the stoichiometry is perfect. I know we end up hitting the equivalence point. That's when I want to stop my titration. Especially for a reaction that's a little bit harder than this, we have to assign these oxidation numbers. So far I practiced with you here, elemental forms are 0. If I have simple ions, just give it the simple charge, H+, so a +1. There are some elements that from compound to compound, they pretty much have the same charge. Alkalis will pretty much always have +1. Hydrogen will pretty much have +1. There were a few examples. Let's say NaH. Well, if I have Na being +1 and I said hydrogen also being +1, wait, their overall charge actually doesn't cancel out. That's this rule here. The sum of the charges has to cancel out. So therefore, one of these has to switch. Because the alkali rule came first, it's the hydrogen that's actually going to switch here. Hydrogen every now and then is going to be -1. Oxygen in a similar fashion, pretty much always you're going to see as -2, but there's going to be a few cases, let's say a peroxide. Notice for oxidation numbers, I always put the sign first in the number. That actually mark you wrong if you put 1+. So I just tell people, just always put sign first in the number. The O, if I try to do -2 there, that would be too much negative charge here. The oxygen actually switches from the -2 and actually switches over just being -1. So there are a few times that an oxygen is just -1. But aside from that, that's how you find oxidation numbers. If the question, lots of multiple choice here, they would just give you a reaction. They just say, who's oxidized, who's reduced, who's this agent, who's gained electrons, who lost electrons, things like that. You should just find oxidation number. You don't bother with the balancing. Because as we saw, balancing here, whether you balance it using the half reaction method or oxidation number method, it was very, very tedious. So in terms of balancing, we want to balance for the number of atoms, like always. We want to make sure mass is conserved. But because we are dealing with electrons that are passing from one place to the other, we also want to be balanced for charge, which is why we came up with a really systematic procedure here. All they're going to ask you to do is just balance. They're not going to force you to balance one way or the other way. We've done examples of doing it both ways. So we can do half reaction method. You break up the two halves, make sure the major atoms are balanced. To balance the oxygens, you add water. To balance the hydrogens, you add H+. We assume that we're actually acidic solution here. For the half equations, we can have electrons. If I have electrons on the right-hand side, it's going to be oxidation. Electrons on the left-hand side, it's going to be reduction. And then when we have the two halves and we want to put them back together, you can actually just do lowest common multiple. We try to do it in such a way that all the electrons end up getting picked up, and therefore it's not charged overall. Okay, so that's the half reaction method. You can try also with the oxidation number method. For the oxidation number method, what you're going to do is you're going to find oxidation numbers of everything. We're actually going to, once you balance our major atoms, you're actually going to balance the charges sort of before you add the waters for the oxygen and add the H pluses. In that case there, the sort of advantage is you haven't broken up half equations. So when we add water and we add H+, we actually add it to the entire equation there. Okay, so let's see if we can practice through a question here. Let's do this one just on the right. Let's go Mn+2 and HBiO3 in becoming Bi+3 and MnO4. Okay. If they don't specify anything, you can assume it's acidic. What if they ask you to do this one here in basic solution? Okay. So again, they're just going to ask you on the test here, balance. Up to you to do half reaction method or oxidation number method. I try to do both for you here. First one here is half reaction method. So let's break up the two halves. So I have Mn+2 in becoming the other manganese compound, MnO4-. I have an HBiO3, which was a fairly easy one for us here because the major atoms are already balanced. One manganese, one bismuth, no problem. Then we go through that memory aid here, major hydroxide, right? So the major atoms are balanced, then balance the oxygens using water. So I have 4 oxygens on the left. Let's add 4 waters on this side. I have 3 oxygens, no oxygens on the right-hand side, so 3 waters. then balance the H's by adding H plus. Now I have 8 H's. I had no H's before, so it's going to be plus 8H plus. I have 1 H already in the side here. I have 3 times 2, I have 6 H's, so I'm going to need to add another 5 H pluses on the left-hand side. Once you have that, the number of atoms should at this point here be balanced. We want to balance for charge by adding electrons. For a half reaction method here, I can see free electrons, so it's the total charge that I want to match up. The total charge on the left is plus 2. The total charge on the right, every H is plus. There's 8 of them. 8 plus minus the 1 plus 7. I'm going to add to the side that has a higher charge to match up these charges here, so I'm going to have add 5 electrons. Oh, the electrons are actually on the right-hand side. This one here is an oxidation. Who actually got oxidized is the reactant that actually has lost electrons. The Mn2 plus is actually oxidized to become MnO4 minus. On the other expression here, I'd expect to see the electrons on the left-hand side. One guy oxidized, one guy reduced. The total charge on the right here is a plus 3. The total charge on this side here is a plus 5. So this one would need 2 electrons. And lo and behold here, that one would need gaining of electrons. It's actually the bismuth that's actually gaining the electrons, but I still quote the entire reactant. HiBiO3 is the thing that gets reduced. So at this point here, your half equations are balanced. As you look later on at a redox table, they actually give you all the equations as balanced. You just need to do this one last step here. Well, because I don't want to have any free electrons in nature, I'm going to do a lowest common multiple between 5 and 2. Both of them go into 10. Let's take this first expression. Let's multiply this by 2. And let's take the second equation and let's multiply this by 5. That's set up so that I actually lose a total of 10 electrons, gain 10 electrons there. So I'm not going to bother with that. I'm going to put all the reactants on the left-hand side and all the products on the right-hand side. So let's just write this down here. 2 times 4 makes 8 water, and I have 2 Mn plus 2. I need to multiply this bottom equation by 5. 5 times 5 is 25. 5 times 1 is 5. Make sure you copy down everything exactly as is, along with the charges and everything. Back to the permanganate, it gets doubled. So 2 permanganate plus 16H plus 5 of your bismuth plus 3 and 15 of your waters. Because we were balancing H pluses and hydroxides on the half equations, very likely you might have some on both sides. So there's no point of having it on both sides. So 25 and 16, let's get rid of this 16. Let's just leave that as a 9. Over here I have 8 waters, I have 15 waters. Let's get rid of that, and let's make this here as 7 waters. Right? At this point here, everything should be balanced for number as well as for charge. Usually I'm running out of time, so I just balance for charge just to make sure. So I have 2 times plus 2 is plus 4, plus the 9 here, it's going to be plus 13. Over here I have a minus 2, 5 times 2 gives you 15, 15 minus 2 here is also plus 13, so we're probably good at this point. So far I've just balanced this here in acidic solution. I'm going to do a similar style here for oxidation number method. Because they specifically say basic, I will not have an excess of H plus around. And all you're going to do as a one last step here is you're going to add, let's say 9 hydroxide to both sides. Yes, the H plus and the hydroxide do cancel out, but they don't disappear. They end up creating waters. And in this fashion here, I actually now have, 9 waters and 7 waters there. I can cancel, make that 2, and drop this. So therefore, in basic, it's actually 2 Mn plus 2 and 2 waters and 5 HBiO3 becomes 2 permanganate, 5 bismuth, and 9 hydroxide. If I did everything correctly, the charges should still be balanced here. 2 times 2 is plus 4, and then I have 15 minus 2 minus 9, so 15 minus 11, so plus 4 plus 4. Everything's good. So that's basic. I'm going to just make a comparison then. What if I try to use oxidation number method? For oxidation number method here, we take the same expression. Again, the advantage is I'm not actually breaking up the two halves. What I'm going to do here is, upon finding the oxidation numbers of everything, hopefully you get a lot of practice with doing oxidation number. You can go, well, Mn is a simple ion plus 2, bismuth is a simple ion plus 3. The permanganate, if the oxygen is negative 2, there's 4 oxygens, that gives you a negative 8. Overall, this has to be a negative 1. Manganese is actually 7 there. H is usually plus 1. Oxygen is usually negative 2. Negative 2 times 3 is negative 6. Plus 1 is negative 5. Bismuth here is actually plus 5. We're actually going to track the changes. So manganese goes from a 2 to a 7. Because the oxidation number has gone up, I know the manganese is oxidized. It's actually gone up by 5. Whereas for bismuth, I went from being a plus 5 down to a plus 3. This one here has dropped. Right? One guy should gain, one guy should lose. It's a little bit weird to think about a reduction as actually gaining stuff. It just turns out the things that I'm gaining are actually negative. The bismuth in the HBiO3 compound here, this is the chemical that's reduced. That's the oxidizing agent. And its oxidation number has gone down by 2. We're going to do a lowest common multiple. So what does 2 and 5 both go into? Well, that's the times 5 and times 2 that we did for at least lowest common multiple step here. We do that part first. Everything that's involved in this plus 5 change gets multiplied by 2. So that's going to be 2 manganese plus HBiO3. Sorry, the other one is going to be times everything times 5. So I have 5 HBiO3. I'm going to have 5 for the Bi plus 3. And then I'm going to have 2 for the permanganate. So somewhere behind the scenes, I've made sure that the gains and losses of electrons, as visualized by these oxidation number changes, somewhere behind the scenes, those charges are balanced. I'm not quite done yet because I still have to add waters to balance oxygens, add H pluses to balance H's. So how many total O's do I have? 5 times 3 is 15, 2 times 4 is 8. I need to add 7 waters to the right-hand side just to make sure the number of O's match up. In terms of H's, I have 14 H's. So far I have 5 already. I'm going to need to add 9 H+, and that should already match up to our acidic equation from earlier. So this equation here. Right? So we had 9 H+ left over after we cancel out the H+. Again, that is balanced and acidic. A little bit more elegant because I didn't have to break up the 2 halves and then try to put it back together. For basic, I had added hydroxide. Another way to convert to basic here is you can actually add the self-ionization of water. If I add 9 waters to become 9H plus and 9OH minus, well, the 9H plus are going to cancel this side here. I have 9 waters and 7 waters. That's going to cancel out. I have 2 waters left over, none of that. And I have 2 manganese, 2 water, 5, 2 permanganate, 5 Bi, 3 plus, and 9 hydroxide. Totally up to you which method you want to use. Okay, so they're just going to say balance. You choose one or the other. Usually I find oxidation number method is a little bit quicker, but although it's a little bit more error prone, this one here is a little bit more systematic. Okay, so make sure you practice some of the balancing there. And then we just started applying some of these oxidation reduction reactions here. In the past, they used to call them electrochemical cells. Nowadays, electrochemical cells is the umbrella term. I want you to actually transition this one here to what's called a voltaic cell. A voltaic cell is running a spontaneous chemical reaction to produce a electric potential. Potential is another name for voltage. It's this is how a battery ends up working. So you punch this into your MP3 player and then it starts running your MP3. There is going to be something that's losing, something that's gaining. Unfortunately, because the reaction is spontaneous, for a voltaic cell, I want half of it to occur on one side, half of it to occur on the other side. Usually we're going to have a metal plate. In general, those metal plates are called electrodes. Those are just conductors. They temporarily hold the electrons. The conductor where the oxidation occurs is referred to as the anode. Notice the definition here. It's the site of oxidation. It's where the oxidation happens. So sure, it could be this metal itself. Let's say metal A. This one here might oxidize. It might drop off its electrons and jump into solution to become A+. Or maybe A is like platinum, it's an inert electrode here. Something maybe just comes up, swims up close to the electrode, drops off its electrons. Still, it's the location where oxidation occurs. The A was just a temporary holding place. The location where that loss occurred is the anode. Electrons will always flow from where they're dropped off to where they're being picked up. The other side here is now going to be called the cathode. So electrons flow anode to cathode. That's actually the location for reduction. So I knew the reaction was going to be spontaneous. The same chemical is here. It's the same reaction even if I had done it in one beaker. But by putting this in 2 half cells, we force the electrons to flow only through the wire. Because the electrons are flowing in one direction, that provides a current. And that's actually where I can actually taper off some of the voltage. Only problem here is usually, let's say in terms of reduction, usually I have chemical B here. It's going to pick up the electrons that arrive here and they actually solidify onto the surface. We can make some observations. Maybe the mass of the cathode increases. We're going to have one side that is at risk of becoming overly positive. The other side here, which is losing positive charges, losing the charges coming down. What we need to do is actually add in what's referred to as a salt bridge to maintain the electrical neutrality. The salt bridge is one last connecting device here. It sort of completes the circuit for us. Usually the salt bridge, we're going to use 1 molar because we want to be at standard conditions. Usually I use KNO3, because the K plus and the NO3 minus ions are so bad at oxidizing and reducing for themselves, they don't interfere with the one that I'm looking for. And in general, what you're going to have is, oh, the side here that was worried about becoming overly positive, let's send in some more anions there. The side that was losing positive charge, let's send in my positives, and therefore we have a generalization. All anions tend to flow towards the anode, and all cations, positive ions, tend to flow towards the cathode. That takes place in solution. Electrons never end up in solution. They get dropped off on the plate, they get picked up on the other plate here, they only travel through this wire. So it's a spontaneous reaction here. On the table, it's written very similar to our acid-base table. These ones here are all written as reductions, so you're going to see is plus electrons. All of the table ones are written as equilibria, because depending on what you're mixing and matching, we might have different comparisons. Because these are all written as reductions, when they give you a voltage, we start off with a voltage fairly high up on the table here. This voltage, I'll give you the first equation. Let's say F2, it gains 2 electrons and becoming 2F minus. I get the standard potential. This one here is a positive 2.87. That's my voltage for my F2. Upon reducing, upon coming to the right, it actually has a gain of 2.87. What if I wanted to do it in reverse? What if I did F minus and going the other way here? I would just change the sign. So that's called an oxidation potential. Just like the acid-base table here, we have, well, all these guys here on the left could reduce. The best guys that reduce, we use the language of being a stronger oxidizing agent, is when you go higher up on the table. So F2 is the one that we have that actually reduces the best. It's the strongest oxidizing agent. We're going to start from the top left and go downwards. You're going to find your first match. I don't care how many other matches you find later on. If you find your first match, everything else is a spectator. For these voltaic cells here, let's say I do actually have F2 in solution here. I found my match here. These ones here are going to be spectators. Then what I want you to do is start from the bottom right. I do need to worry about the thing that's oxidizing as well. That's also categorized as a stronger reducing agent. So start from the bottom right and you want to find your first match. Once you have that match, that's the best guy oxidizing. Notice I'm fairly low down the table here. That means my reduction isn't occurring as easily. My partner has an easier chance of coming forward. Again, I don't really care how many other things that might potentially oxidize. Once I found my match, the other ones are spectators. You're going to find for the first little bit voltaic cells, you're going to find your reduction reaction happen above your oxidation reaction, and therefore the overall voltage is positive. That's the total voltage that your battery can actually give you. Now, technically speaking here, we always have to have anode and cathode for a working battery. It's a little bit weird for me to be able to say, well, here's a half cell and suddenly here's the voltage. What we did is we chose one cell to be our reference. It's right in the middle of our table here. That standard cell is called the standard hydrogen cell. It's called the She. And basically it involves H plus as the ion that's actually reducing. We're going to assign this one here 0 volts. So if this one here were 0 volts, what does it mean if the fluorine has positive 2.87? It means it's actually 2.87 better than H plus. Then what if I get lower than it? What if I go right down to the bottom here? I have Li plus and an electron coming forward becoming Li. Well, that one is quoted at a reduction potential of negative 3.04. Well, that'd be silly to use a battery that actually needs voltage. That's actually a positive voltage, but why I'm saying negative is relative to my reference, it's actually worse off than hydrogen, 3.04, so it's 3.04 volts worse, less voltage than the She, worse than the standard hydrogen cell. Okay? All these standard potentials here, the standard here is given by that little naught symbol. They're all at a sort of consistent environment so that I can make a fair comparison. So standard for us is going to be 25 degrees. 1 atmosphere is nowadays going to be switched over to 1 bar of pressure. Probably most important here is 1 molar solutions. When your battery is still fresh and has lots of chemical present, over time as the battery ends up using up some of its chemical, as the chemicals decrease, the battery's voltage will also decrease as well. Okay? So some of the notes here, if you reverse the reaction, you flip the sign. That's going to actually allow for you to get an oxidation potential. Potential for voltage, they're all written for reductions, they're all written going left to right, but oxidation is going from right to left. The surface area of the electroplate actually doesn't affect the voltage because the concentration of solid is constant. It might affect sort of how much solid actually gets coated over time here. It might affect how long the battery can run for, but at least the voltage E cell that we carry doesn't change. Okay? As the chemicals gradually deplete, the reduction potential drops, the oxidation potential increases here until there's no other difference. When the E cell is actually 0, there's no desire to go forwards anymore. We're actually at an equilibrium. That's when we actually have a dead battery. Okay? So make sure you have a look at some of those notes there. Pretty much we're setting up in such a way that I can taper off some of the electrical energy. There's some sort of examples in your workbook here. A breathalyzer test. So breathalyzer test takes chromium from a +6 state. Chromium is actually going from an orangey yellow color down to a chromium +3 state. Now +3 is actually dark green. This one here is actually our beverage, just drinking alcohol, which one is actually an ethanol. This one they're actually carrying, there's a legal limit for how much alcohol can be in your system as you go behind the wheel. So if you breathe into this equilibrium, if there's too much alcohol in your breath, it reacts to the chromium, it converts the orange way more into the green. The police officers can just have a meter, well, how green does this solution end up getting, and actually validating how much ethanol is actually in your breath. Lead acid storage battery. So this one here is a car battery. It's sort of like a disproportionation where we have one chemical actually undergoing both oxidation and reduction. In this case here, it's actually the reverse. The lead, going from a 0 state to the +2 state here, lead is oxidizing to become that, and the PbO2 going from +4 down to 0, that's actually reducing also to become the same chemical here. We have our 2 metal plates here. For typical batteries here, we play around with the different different states. Sometimes we make the battery background out of a moist paste versus like a liquidy cell like this, so that if I knock the battery over, I don't have to worry about, oh, now the water's not touching the electrode, now it's not working anymore. So you could engineer some of those aspects. For the lead acid battery here, this PbSO4 actually occurs as a solid state. It actually starts coating the lead plate and the PbO2 plate that I actually wanted to react. At that point here, if the plate here of Pb and the plate here of PbO2, if they're no longer touching the sulfuric acid, which is the other reactant that's needed, that battery would need to be jump started. Usually your car batteries, as you run your engine, usually the car battery, not even an electric car, but usually as you run your car, it is constantly trying to recharge the battery. It burns some of the gasoline and reconverts it. And basically what it's trying to do is it's trying to get rid of some of this deposit of PbSO4 to try to have a fresh lead surface to actually touch the sulfuric acid so the battery can actually run longer. We have some other types of cells here, a zinc carbon battery. These ones here are more your AA batteries here. You should be able to identify based on oxidation number here, what's the oxidation and what's the reduction reaction. As we sort of leave this voltaic cell section here, we wanted to deal with corrosion. Corrosion was rusting. For rust to form, we actually have metals actually having the oxidized state. So rust actually takes many different formulas here. It could be iron 3 oxide here, it can be iron 2 oxide, it can even be iron hydroxide, things like that. But pretty much the thing that corrosion has in common is your metal has been oxidized. It's now put in the +2 or the +3 state. How we can prevent it here, the sort of ingredients that we need for rust here is, like I mentioned, it has to oxidize the metal, and you have to usually be in the presence of water, be in the presence of oxygen. So one easy way is, let's apply a layer that actually separates. Say I have an iron surface, and say I actually apply a non-polar layer of paint. Well, if the oxygen is out here and the water is out here, they can't actually touch the iron surface, so therefore no rust. That's why people are really worried when the paint actually just chips. Well, big deal, it's just such a tiny chip there. Well, when there's a chip like that, basically the iron is not exposed to the oxygen in the water. That's a situation where it might rust, and it might actually start rusting below the paint as well. That's why very quickly they want to just sort of paint it over to try to separate the oxygen from the water. There are other ways of doing this as well. We do see iron on the table. It's fairly far down on the table. So we have Fe. I'll sketch a few lines for you here. Fe plus 2 and 2 electrons. The reduction potential is negative 0.45 volts. If I have someone else oxidize, so let's put down another plate here, Li2 plus and 2 electrons and nickel like this. And I'll give you one on the bottom. Aluminum plus 3 and 3 electrons become aluminum. The goal is to keep, let's say iron is the metal that you want to be protecting. The goal is to keep iron in the reduced form, right? because we have NOx cared, right? The reduction should occur at the cathode side. So that's why sometimes we actually refer to this as cathodic protection. If I'm worried about having iron ions, I might put in some solution of Ni2+. Well, it's the Ni2+ that's actually going to reduce. In that case there, the iron would be a spectator. Well, that's actually the opposite of what I want. I want to get rid of the iron. So instead of having the Ni2+ here, let's let the iron +2 stay reduced, and let's force something else to oxidize. The worrisome bit was if the iron oxidizes, it's going to end up forming rust. What if I link my iron? What if I connect it to a piece of aluminum? Well, something's going to rust. If I have a piece of aluminum, it doesn't need to be very large. Between aluminum and iron, who's going to oxidize first? Aluminum is a little bit lower down on the table. Remember, the strength is actually better as farther down you go. It's actually the aluminum that's going to oxidize. That's going to allow to keep the iron in the reduced form. So those are ways to cathodically protect this iron here, connected with something else that's more willing to oxidize. We actually sacrifice this anode. Something is going to rust, but it's not going to be my iron. Okay. Lastly here, we switched over. Remember, electrochemical cell nowadays is the umbrella term. So far, we've been looking at a voltaic cell. A voltaic cell is spontaneous. The E cell, the total voltage after you add up the reduction and oxidation, this one here was positive. Now we're going to switch over to electrolytic cell. Fortunately for us, it's exactly the same table, but an electrolytic cell, this one is a non-spontaneous reaction. This one here, when you add up the E cell, it's actually going to give you a negative voltage, so we could actually put this all in the same container together. The chemicals don't react anyways. What we need is we actually need an external power supply. Now, even for the carbide, it looked like an electrolytic cell. This one is a spontaneous reaction. I don't need a power supply. That's the other thing that I need. For the power supply, we go long line, short line. The long line is the positive side. The short line is the negative side. The positive side is the anode. The negative side is the cathode. Because if anode is the site of oxidation, if that's where electrons get dropped off, I need to have the positive end to draw up the electrons. As the electrons get pushed through the battery, the negative end pushes them along. Again, electrons still flow anode to cathode. That was true for both cases, anode to cathode, and that is through the external wire. The electrons never enter solution. I don't need a salt bridge because they're already all in the same container together. For this one here, also really systematic. All you're going to do is you're going to state the species present, okay, exactly as is. So let's say this one here was, I have 1 molar LiBr. Okay, so if I'm going to state the species, the 1 molar, careful, water is really annoying in this section. 1 molar, or the aqueous, refers to there's water present. I have LiBr. I'm not going to see this as compound. Well, in water would have separated Li plus from Br minus. So I actually have Li plus ions and I have Br minus ions. So I have these 3 chemicals. Potentially my electrodes might react. Let's say one of them here is platinum. Platinum and carbon are inert, so don't worry about them. Let's throw on maybe a copper plate as well. So copper potentially could be a reacting electrode. So once you make a list of these are the chemicals that potentially could do the reaction, you want to look for an exact match. So on the table, we're looking for copper metal. Water appears a couple times. Lithium as an ion. I have Li plus. I do not have lithium solid. I have Br minus. I don't have Br2. So second step here is you just check the table. As you look at the table, I'm just going to hint at what the table looks like here. We're going to always start from the top left because these ones here are the best guys at reducing. Start from top left on the fluorine side here. As you work your way downwards, let's see what we end up seeing. I end up passing by a Cu plus 2. Can I use that? Well, no, I have copper solid. I don't have Cu plus 2. Keep going. So you keep going here. We do end up running into water because we're actually so bad at reducing. I'm actually 2/3 of the way down the table here. I do have a water equation. I do have another water equation. And then finally, the Li plus is actually sort of the last entry down. So between all these guys here, and I don't have the copper, between all these guys here, who's going to do the reduction? Well, water is the highest up on the left. So this one here is actually going to do the reduction. On the table, they actually write this for you as an equilibrium. Once you've decided it's going to be the reduction, so just one-way arrow, this ends up forming H2 and 2 OH minus. There's the pesky little 10 to the -7 molar. The standard reduction potential for that one is given as a negative 0.41. That's 0.41 worse than the standard hydrogen cell. Then what we do, so we start from the top left. Write that down for you here. Start from the top left and start going downwards. Then you start from the bottom right. We need to have both some guy reducing and some guy oxidizing. Oh, I run into lithium. Can I use it? Well, no, I have lithium ions. I don't have lithium, so just keep going. Keep going, keep going, keep going. On this side here, we do actually happen to run into copper. Then comes another water, then comes another water, and then we have bromide ion, 2Br minus like this. So because I started from the bottom right here, you find your first match here, copper is going to do the other reaction. Copper actually is going to do the metal plate that actually reacts. So again, on the table is written as an equilibrium. I know it's oxidation, so copper is actually going to form Cu plus 2 and 2 electrons. The reduction potential, the going left to right here, this one here is actually going to be positive 0.34. What I need to do is I need to flip that voltage around. If I have instead Cu becoming Cu plus 2 and 2 electrons, the voltage switches. It's totally possible that these reduction potentials or oxidation potentials may be positive or negative, doesn't really matter. But when I add them up together, the overall E cell of the entire electrolytic cell, when I add those two up, I'm getting negative 0.75 volts, right? And this one here, overall, we need to input positive 0.75 volts to run the reaction. The reaction just simply doesn't go by itself. I need to supply that voltage. Because of losses due to efficiency arguments, things like that, usually I know I need to put in maybe 5 volts to actually get the 0.75 that I actually end up needing. Now, just one other comment here. Let's say copper wasn't actually in solution. It would have been water reacting both ways, and totally no problem. Water has that overpotential effect here. It was an exception where while I do run into water before the bromine, there's a little bracket here that ends up actually showing you these Br minuses experimentally actually oxidize before water does. So if copper weren't present, or if I ran out of the copper, not anytime soon because this is solid, the Br minus here, because of overpotential, due to overpotential, if copper were not present, which I know it is, the Br minus experimentally oxidizes before water. So just watch out for that one there. Anything that's sort of captured by the bracket actually reacts before the water does. And really, when I've been looking at questions, they really only ask you chloride and bromide. When those ion concentrations are high enough, they're going to actually perform the reaction before water does. Looking at the product side, you can give me some conclusions of what ends up happening. So our reaction involves copper solid and becoming copper plus 2. I would expect the copper, that's the oxidation reaction, have it hooked to the battery properly. Perfect. Copper is going to jump into solution, becoming copper 2 plus. I'd imagine this mass here is going to decrease because I'm going to lose copper solid particle. On the other side, the water just swims up close to platinum. The platinum is just a temporary holding place for electrons. The electrons just arrive here. When water gains those electrons, it ends up forming H2 gas. Whenever gas is formed underwater, we're going to actually have bubbles just on the one side here. And we also form hydroxide. That would have made me say it's going to be basic. It turns phenolphthalein to pink color, but they do remind you this 10 to the negative 7. That's nothing more than a neutral solution, what water would have done self-ionizing anyways. Okay. And there were two other applications. Pretty much you just want to keep the goal in mind. And electroplating, the whole notion is to plate something onto something. So let's say I have a spoon and I want to add something on top of its surface. Maybe I want to coat it with nickel surface or something like that. So what you want is you want ions to actually reduce on its plate. So you actually want this one here to be the cathode. Or if I have electrorefining, I might have a block that is very, very impure. This blob here contains many, many different minerals here, maybe some A, some B, some C like this. What you're going to do is you actually want this to be the anode so that you can actually slowly rip off, maybe the A comes off first, and then after the A is all gone, then you can pull out B. I want that to be anode. We're going to be a little clever with what happens on the other side then. Well, if I want to plate out, let's say chemical D onto this plate here, maybe I also make the anode out of chemical D, so that will constantly replenish the D ions in solution. Or over here, as I pull off A+, that's going to be the anode, that's going to be the positive side of the battery, the long line side of the battery. Maybe I'm going to have a plate of A, so that when A+ is forced to reduce over here, A+ actually just gloms onto a pure block of A as well, and that way you've done the sort of purification. Okay, so just some applications of electrolytic cells, exactly the same table, but by the time you find your first matches, you're going to find that the reduction reaction, the one going left to right, is actually lower than the one going right to left, and therefore it's non-spontaneous overall. You need to put in some external voltage. Okay, so let me know if you have any questions. Thanks, guys.